Okay, so today we're going to continue talking about functions, but we're going to start talking about them in a larger context, where you're starting to do error handling between function calls. So, like for example, when you call a function, it can report back to you that an error occurred. You gave me bad inputs. So I'm going to throw it back at you as either an error or an exception, depending on the language that you look for, or that you're considering. Errors are things that can be completely unexpected or anticipated but not normal. For example, missing a file. Your program is supposed to open up a file and start processing the data in the file. That file is not there, or you don't have permissions to view it. Or it's corrupted in some way, right? It could go wrong a million different ways that you could anticipate, and then you could write code to handle that situation, and that's what's called error handling in general. Some errors are by nature fatal. If instead of opening a file, you could be connecting to a remote database, and you have no internet connection. Is there any way that you can write a program that fixes your internet connection? Probably not, right? Some errors you can recover from, probably not that one. You can anticipate them and not perform a dangerous operation before you're about to do it. For example, division by zero. If you're about to divide x by y, check to see is y 0? If so, don't divide by 0 and do an alternative. That might be a fatal error, right? You quit out of the entire program. But ultimately, you might be able to handle that situation. Division by 0 leads to a very, very large number instead of infinity or nan or something like that. This is known, again, as error handling. You handle the situation in the event of an error. Okay? Both languages use very, very different approaches. C uses, there we go, uses what's called defensive programming. And this is programming. This is just simply characterized as looking before you leap, right? So what you do is you write code that you can anticipate. You write code to detect potentially bad or dangerous operations. For example, am I about to divide by 0? Is there in fact an internet connection? If not, then don't try to connect. Do something else, right? Is the password bad? Okay, well then reprompt them for the password. Reprompt them again, reprompt them again. After the third time, maybe then that's fatal. Kill the entire program because they clearly don't know their password. They need to go and reset it or something, right? If they would occur, you don't do them, do the operation, right? Instead, within a function, you return an error code, right? So what is an error code? An error code is simply an integer, right, value that represents the type of error that occurred, that would have occurred, right? By convention, 0 is usually means, just like 0 means false, it's the only thing that means false. 0 means no error, right? 1, 2, 3, etc. Right? Any non-zero value indicates some type of error. 1 would indicate an error of type 1. 2 would indicate an error of type 2, etc. Right? And giving these semantic meaning, we're going to talk about that too. Semantic meaning, as in, these are just magic numbers. Where the heck did they come from? 1, 2, 3, right? And you don't want a program like that because those are mysterious numbers that you have no idea what they stand for. Instead, you want a different human-readable English term for each one of these things so that you don't have to have that guesswork. What was error code 1? What again? I don't know. I don't remember. What was error code 2 again? I don't remember. Right? Always having to look back at what the error codes were in your documentation means that you're wasting time. Right? So instead, we're going to associate them with human readable English terms, right? Non-zero values, though, indicate some type of error. Now, Java takes a completely different approach here because Java is a modern programming language. The vast majority of modern programming languages, by the way, do use what are called exceptions. Right? So again, modern as in, I mean, programming's not that old. I think Fortran was invented in the 50s. That was the first real high-level programming language. So we're only talking about 70 years here. C, of course, was only came like the full C version was 1980 or something like that, very late 70s. So we're talking only 40 years there. Java is only 25 years old, right? And new programming languages are being created all the time. So modern programming languages support exceptions. Right? Exceptions take a completely different kind of view. So with looking before you leap, you're walking along and you look, oh, am I about to step in a hole? Or am I about to step off that cliff? Right? Exceptions say, go ahead, keep walking, don't worry about it. Because what you can do is you can go ahead and attempt to perform dangerous operations without looking, right, before you leap. But it's okay, because if an error or exception occurs, it will catch you. And I like to use this analogy. Ooh, sorry. I like to use this analogy because the keyword catch there is actually used in your programming languages. You try something. In fact, it's okay. You can go ahead and attempt. Let me go ahead and remove that word. You can go ahead and attempt to try to perform that dangerous operation. And it's okay because if an error occurs, it'll catch you when you fall and then put you back up and then let you decide what to do, right? You use the keywords try, catch to do this, right? All right, so those are two basic approaches in each programming language. Today we're going to focus on doing this in C, okay? So in C, you design functions. Sorry, here we go. Let me give myself some more room here so that it snaps up. There we go. All right. So in C, you design functions such that the actual return value is freed up. For example, you want to return the monthly payment, and we'll do this as a demonstration here. You want to compute the monthly payment given the annual rate, the balance, and the number of years, right? So there could be many bad inputs for that. We want to communicate those bad inputs back to the calling function. So what you could do is, but how do we communicate that back to the calling function? What we'll do is instead of returning the monthly payment, we're going to return that, and I'm doing double quotes here, we're going to return it as a pass-by reference variable. Remember that pointers, right? We're going to give that function a bucket, and they can put the result into the bucket, which frees up the return value to return an error code, right? So because it's been freed up, again, you can make it into an integer function that returns what type of error might have occurred, right? And again, in general, 0 indicates no error, and we don't want to use magic numbers. So let's go ahead and just jump right into this as a demonstration, using some sort of a demonstration here, okay? I'm going to go over here to utils.c, and let's think about this in terms of this function. So what are the types of errors that could occur? What are some bad inputs that you could give to this function? Don't worry about the main, about somebody typing in bad inputs, right? We're going to handle that in this function, and we'll talk about that why in a second here. Yeah, go ahead. All right, so negative values on, say, the annual rate, right? Anybody ever heard of a loan that pays you interest? That's called a, that's what, say what kind of it?
That'd be nice.
Yeah, that'd be very nice. Borrow as much money as you can. But that's called a savings account, right? You're loaning the bank money, and then they pay you interest. Not nearly as much as they charge you, though, right? That's what a bank is. So annual rate, if that is less than 0, right? What about less than or equal to 0? Is 0 a bad loan rate? I'm not from the borrower's perspective, certainly, but also it's not uncommon. You see 0% interest for 6 months, or 0% car loan as long as you buy a $50,000 new car, right? Yes, we'll give you a free loan as long as you're overpaying for a car. I drive a Fit, and I got the last one, or I got the last year model before they discontinued it. That's still a car that that's I think 14 grand for a brand new, right? And unfortunately, I can't find a replacement for it in 5 years because every single car that I've looked at since then is at least 20 grand. I'll probably buy used from now on. Right? All right, so if the annual rate is less than 0, is there another end that would be invalid? Remember, the annual rate is between 0 and 100%. All right, so you're paying more than 100%. Does that sound right? Probably not. So, or annual rate exceeds or is equal to, say, 1, right? Now, in real life, there are usury laws that prevent, 50% interest loan, right? That's usury, that's loan sharking. But I don't know, we're not going to handle that here, right? 100% interest, you might be able to pay that down, but I think that certainly if it's greater than 1, I think that you could never hope to pay that down. I'm not sure. But in any case, so this is an error, right? We're going to have to handle that situation. What's another type of error? Say with the principal. Does it make sense to borrow negative $500? Probably not. Does it make sense to borrow $0? Can you walk into a bank and say, give me a loan for $0? They'll say, okay, well, here you go. Here's nothing, right? So maybe the principal needs to be positive. If the principal is less than or equal to 0, then it's a different type of error, right? We'll come back and fill these in here. Else if, what's wrong with the years? So do you remember, I don't have the formula here, but remember that we raise it to the negative years, right? And it's 1 minus this thing. Well, if I raise it to the 0, this becomes 1, and in the denominator, I've got 1 minus 1. What would I end up doing in the denominator? Divide by 0, right? So can I have a 0-year loan? Probably not. Can I have a loan that I can pay back in negative 5 years? Right? That would be me going back in time 5 years to pay it, right? No, that doesn't make any sense. So if the years is less than or equal to 0, then it's yet another type of error. Right? Let's go ahead and that's good enough for now. Okay. Otherwise, we'll come down here and compute that monthly payment. Okay. Now, how do I communicate back to the calling function that it was this type of error? I'm going to return an error code. Return 1. Error type 1. Right? Now, we'll take care of the fact that this is a mysterious magic number here in a second. But if it's a different type of error, should I be returning 1? No, I should really return 2. Right? If I could return negative 1. Right? Any non-zero value is going to be an error code. But we'll go ahead and return 3 here. Now, in the event of no error, by convention, I should return what again? Return 0. Can I do that though? No, I've got 2 values that I want to return to the calling function. Whether or not there was an error and what the actual monthly payment is in the event that there's no error. Go ahead.
Wouldn't your function already be terminated?
It would be. I can't do something like this, right? So in fact, it's probably going to tell me that if I tried to compile this, or there'd be a warning about this, that you have 2 return statements. Okay. By the way, in mathematics, can you do this? What is a function? All right. So x squared, that's a function. It's a concave up parabola, right? Is a circle a function? No. Why? Because for one input, say 0, the unit circle, it maps to 1 and negative 1, 2 values, right? Can you have a function that does that? Is the circle a function? No. It fails, what is that called again? The vertical line test. Likewise, this fails the vertical line test. It's a function. It can only at most return 1 value. It could be a void function and return no values, but you can return at most one value. So we can't do this. So what do we do instead? Okay, I'll go ahead and change this to result temporarily. I've got this result. I need to give it back to the calling function so that it has, in the event that there was no error, it also has that $188.71 that we were playing around with. Right? How do I do that? I need to give it a bucket to put it in. So int result, or not int, but double. Now, is that a bucket? Nope, that's just a regular old variable, right? That's like giving the get monthly payment the result. Why are you calling that function if you already have the result? Right? You want to give it a bucket so that this function can put the result in the bucket, meaning that I want a pointer variable. Okay? And we probably shouldn't call it result. We should probably call it monthly payment. Okay. Once I've got the result, how do I get that into this variable? Monthly payment is equal to result. Is that correct? Yep. Well, what do I need to put in front of it? This thing is the thing on the right-hand side is a regular old variable. The thing on the left-hand side is a pointer. So how do I make this pointer into a regular old variable? Careful. Star. Right, you'll just have to commit it to memory at some point. Right? Once you start using them next week, you'll get used to it. I could have also have done this, or could I have? Monthly payment is a pointer. Ampersand result, that changes the regular old variable into a pointer variable. But is this going to work? Where does result exist? Remember how functions work? Stack frame, stack frame, stack frame. Where does result exist? In get monthly payment stack frame. When if you can make a pointer point to that if you want to. It's your memory. You can do with it what you want. But when you return to the calling function, what happens to that stack frame? Pops off the top, thrown away. What are you pointing to now? Right? Who knows? Right? So you can't do that. You have to provide the pointer and put the bucket and put stuff into that bucket. That means that we don't need that return value type anymore. We can change that into an integer. Right? All right, we're passing it by reference so that we can compute the result. And by the way, we don't need to store it in a temporary variable here. We can go ahead and change this so that we don't have a superfluous variable here. Right? There we go. Sometimes it's better to do it like this if you need to wrap your head around it. If it's a result that you update and it's really complicated result that you have to compute, then set it at the bottom once, right? And I usually do that as well. Okay. Now let's go over. Of course, we're going to have to change the header here and the prototype, excuse me. And the documentation for it too, right? Because we've changed the signature of the function, we've changed the behavior of the function. This function computes the monthly payment of a loan, right? Given the inputs. What else does it do? It places the computed result into the pass by reference variable. And I'll call that the monthly payment, right? Because that's what it's called. In the event of an error, it returns a non-zero error code. Right? Now, that's the convention. So if you know C already, I wouldn't put in that kind of documentation. But I would put in the kind of documentation that, what are the errors? Right? So to do, document the type or the types of bad input. And because we're going to throw it back at them. I'm not going to compute something that would result in division by 0. That is an error dealing with your years, right? Years cannot be negative. So I'm going to return 3 to you, right? All right. Let's go ahead and, oh yeah, go ahead.
Is it just best practice instead of returning like your value that you want to
It is usual practice, yes. Let's take a contrary example. When you call the square root function, what is a potentially bad input for the square root function? -1, right? Because it doesn't support complex numbers. That would result in not a number, right? And if not a number times 5 is still not a number, right? Now, there is some error handling that's going on under the hood. There is this error code, there's this global error code variable that then gets set to one of 3 values. And we might talk about that later on. I'm thinking of cutting it, but EDOM, ERange, and ESquilax, kind of, I forget I don't even know how to pronounce it, but EDOM means that it's an error with the domain of the function. What is the domain of the function? The input, right? Domain maps to, what's that other thing called? The range. There was an error with the domain, there was an error with the range, right? And so an EDOM error would occur because you gave it a negative value, right? Or maybe it's an ERange, I forget what it is. Log of 0 is undefined because it's not a number, but it is a number, but it's negative, infinity, right? 1 divided by 0, well, that's positive infinity, right? And there's this other error code that you can access that gets set, but square root doesn't return that error code. It just goes and sets this error code that then you can go and look at that if you want to. This is the convention, though, because that's system-level error handling. And we shouldn't, unless we're systems programmers and changing, how C works or whatever, we shouldn't be touching that, right? We have we're in user space, we're defining our own library, and so we're going to use this convention in our library of returning an error code and then returning the actual computed value in a pass-by-reference variable. For those of you that did the C version of the lab yesterday, you were working on images, right? And you were converting RGB values in an image to sepia, say. Remember that you had 2 sepia red, 2 sepia green, 2 sepia blue, RGB values, right? Why did you have to have 3 functions? Because you can only return 1 value. If I want 3 values, what do I need to do? I need to pass in 3 buckets. And that's what you're going to do in your lab next week. If you do the C version, you should do the C version. Okay? All right. So let's modify it and use it here. There's the monthly payment. I no longer capture the return value. Instead, the return value is an integer, right? Error. And I pass in the monthly payment as the 4th argument there. Now, is that correct? This is what type of variable is monthly payment? Well, the parameter is going to be a pointer. It expects a pointer, but is monthly payment here a pointer? Nope. So, attempt 1. Make it into a pointer. What is it pointing to? Nothing, null, garbage, a memory location that doesn't exist, a memory location that doesn't belong to us. If I gave you a bucket that didn't belong to me, right, what's that going to end up being? A segmentation fault. So let me go ahead and get rid of that. That attempt didn't work. And what should I have done when I passed the variable? How do I take a regular old variable and make it into a pointer variable? Ampersand. Just like scanf, right? There we go. All right, so let's go ahead and test it. We can test this out as long once we do the error handling. So if the error is of type 1, what type of error was that? Does anybody remember?
Negative annual rate.
Okay, so invalid annual rate. You've got a better memory than I. All right, and then we'll go ahead and exit. Say with the same error code. 1. All right. Else if, why would we exit? You gave us bad input. I couldn't even compute the monthly interest or monthly payment, so there's no reason to go on. Right? Go ahead and just exit. Else if error is equal to printf to do. I forgot which error this is. Right? There we go. And then we'll exit with an error code of 2. Right? Else if it was a different error code, error is equal to 3. Then yet again, I forgot which one this was. We'll go ahead and just exit with 3. Oops, there we go. 23. All right. Now, I think I do remember which ones they are, but I'm trying to drive home a point here. You have a bad memory. Are you going to remember what 1, 2, and 3 stood for? You've got a more complex program where you've got potentially 100 different errors. Are you going to ever remember the list of errors that you wrote out? Nope. Even if they're small, 3 errors here. Come back in 3 months. Take a look at this this code with fresh eyes. Are you going to remember what the hell those stood for? No. Right? So we're going to have to fix that. Before we do, what I want to do is I want to come over here to the utils, and what if instead of returning 1, we exited with an error code of 1? Does that sound like a good design kind of approach, a strategy? By exiting, what have I done? I've terminated the entire program. Me, the function, get monthly payment, I'm the function now, has decided for you, the user that's using this function, what to do. Right? I've taken the decision away from you on how to handle this error. Right? Instead, what I should be doing is informing you of the error. By the way, there's something wrong with your annual rate. You decide what to do. If you want to decide that that is a fatal error, great, go ahead and just exit. If you want to decide to reprompt the user for better input, that's your decision. If you want to use a default value, like 5% or something like that, as a placeholder, that's your decision. By exiting within a function, I have taken the decision away from you. Bad design. If you call square root on -1, does it kill your entire program? Nope. Your program is only killed by the operating system when you have something like, say, a segmentation fault. You're doing something highly illegal, segmentation fault, you can't access that memory. Right? That's really the only time that a program should probably be terminated, right? Without your, affirmative decision to end the program. Okay. All right. Here's another bad design approach. Printf. You have a bad annual rate. So I'll return 1. So I won't just exit on them, but I will also print an error message to the standard output. Does that sound like a good, solid design approach? Why not? One, I'm still taking a little bit of the decision away from you, right? And 2, what? What else? Yeah, it should be, what if it wanted to print a different error message, right? Also, nobody's sitting at the terminal, right? 99% of software is written to interface with other software. 99% of software is not sitting there waiting for a user to read what's going on and respond to it. That's the whole reason we write software to begin with, is to automate things. Now, if your automation is pumping out millions and millions of lines of error messages, right, that nobody is looking at, who cares, right? Don't do that. Right? Now, there are use cases for doing that where you want log messages, but the standard output is not the solution for that. You would want to make an affirmative design decision to collect all these log messages. User XYZ just logged in. User DEF just logged out, right? All those events, that would be, you'd want to use a proper logging system for something like that. You don't want to do that inside of a function. Square root doesn't print out, you can't give me negative values, and then returns NaN, not a number, right? So we're not going to print anything in our function either. Good. All right. Again, I don't remember what these are. So what I'm going to do is I'm going to define what's called an enumerated type. Type def. I'm going to define a type. I'm going to type def, right, definition. An enum. Enum is short for an enumerated type. Now, what's an enumeration? It's kind of like a declaration, but it's an enumeration. Here's the first thing. Here's the second thing. I like cake. I like ice cream. I like donuts. These are listing all the things that you can go ahead and bring bring to me on your bring food to the professor day. There is no such day. But an enumeration is a list, right? You might have seen it as a bullet pointed list. You might have seen it as a numbered list, 1, 2, 3, 4, right? An enumeration is a list. So let's list all of those types of errors with plain old English names. So what was one of the types of errors? Invalid, what? Invalid rate? Okay. Annual rate, oh, okay, I like that better. Annual rate, okay. Comma. What else? What other type of error did we identify? Invalid, what? Principal, okay. Invalid, what was the last one? Terms, years, whatever you want, comma. All right, well, we also had no error, right? Where should that go? So remember, this is 1, 2, and 3. But no error was 0. So if you're going to have a 0, where should you put that? Probably at the top, right? No error. Okay, there we go. I also need to give this a name. Let's call it an error code, because that's what it is. Semicolon. This is an enumerated type. It's a list of things. If you have an occasion to define something that can only be these, say, 7 things, like days of the week, Sunday, Monday, Tuesday, Wednesday, all the way through Saturday, or months of the year, they're not adding any more months in the year. They're not adding any more days in the week, right? This is an enumeration, and it's a list of things. The syntax here is, of course, type def, and all one word, enum, short for enumeration. And then you have an opening curly bracket and a closing curly bracket. And then finally, the name of your enumerated type. If I did this for months, I would call it months or month. If it were days of the week, I would put in day of week, all right? And then within that opening and closing curly bracket, that's where you put the list. White space doesn't matter. You could do it like this, right? You could put it all on one line. But is that really all that readable? Now, this is much more readable, 1 to a line. And it's like a real enumeration. Bullet point 1, bullet point 2, bullet point 3. Yeah, go ahead.
So for the error code name of enumeration, you use upper?
Yeah, these are conventions that I'm hinting at, and then we'll note them when we write up the notes here. So these are all uppercase underscore, and then the name of the enumerated type. The convention I'm going to suggest to you is to use upper camel casing. Right. Yeah?
Should you do this, the same like white space thing with the prototype for your functions, like if you have multiple parameters?
Oh, like this? So often people will use this kind of convention where they align all these things up, right? And that's perfectly fine too, so that you avoid really, really long lines, right? And usually it's done, you do it by aligning these right here. Some people go even further and align all of these things so that the names also line up, right? And then some people like to put spaces here. I don't like that because I like it a little bit more compact. This is okay. I wonder what a style would do to this. So a style of utils.h. Oh, okay. It's fine with it. It left it. Yeah. Oh, but it was not fine with my 2 spaces. It changed that to a tab. I disagree. It should be space. Oh, it didn't do it for the first one. Fine. There. space, 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 space. There we go. Right. I prefer that. A style prefers tabs apparently. Right. And then you can get into a holy war with people who prefer tabs versus people who prefer spaces, right?
Is it difficult to customize your A style?
I don't know about A style, but it's certainly not difficult to, whatever formatter you use can be, you know, like C formatter. I think that this is probably the one, yeah, code beautifier. This is the one that I linked to in Canvas. You can, well, maybe it is, I don't know what it is. Let's find out what it does. So here we go. And it did not like the fact that I indented all the way over there. So another convention that some people use will be to even put the first one on the next line and do something like that. Right? Again, it doesn't matter as long as you are consistent about what you're doing. Right? But yeah, you can avoid long lines like that.
But when you're calling a function like that, you probably wouldn't.
Probably not, because that's not going to be that long of a line. But you can. Some people do, and it really depends on. You know, you do want to avoid long lines, right? But you don't want to bend over backwards to avoid long lines. Right? Okay, now we can actually use this. Let's go back over here, and instead of returning an integer now, what do we return? An error code. Right? Instead of returning 1, what do we return now? Well, what did I call it? I forget. Invalid annual rate. Invalid principal. Invalid years, I think I called it. Right? And then instead of returning 0, I'll return no error. Right? And I can do the same thing over here in loan.c. Instead of looking at those as magic numbers, I will look at them as human readable error codes. There we go. And invalid year. And now I remember. Oh yeah, that's an invalid annual rate. So annual rate must be in 0 to 1. Right? Oh, and then I guess exclusive on the 1, right? There we go. Yeah. Oh, I did. Thank you. Annual rate principal. There we go. All right, I will move this error message up here, and then invalid principal, and invalid years, bad years, whatever, right? More human readable terms here. You can write your own essay if you want to. I'm not gonna. Okay. So let's make sure that it works still. GCC -c for utils.c. Remember that's compile without linking, right? Oops, I did forget to change error code over here to this error code right here. Right? And there maybe is an argument for not aligning it like that, because if you ever go and make changes, you're going to have to, all right, tab over a little bit more every single time. Go ahead, question.
For the Unix commands, you have to do the GNU 99.
Not in the CS50 IDE, because I think that's the default. If you're on CSE, yes, you do, because that's not the default. Right? Yeah.
Did we change the error code in util C as well?
Yes, we did. I did. Yeah. Yep. And now we can compile it all together. Utils.o and loan.c -lm if we use it. And $10,000 at 5% interest over 5 years gives us the same output that we've been playing with. But now, say, negative $10,000 gives us an invalid principal. A 200% interest rate gives us a different error message here. And then finally, negative 5 years? Bad years. Okay? We were doing all of our error handling inside the function. Yeah, go ahead. Well, you can exit but I'm exiting is okay here because I'm in the main. You would never probably exit within this function. Now, exiting with an error code is basically the same idea. The entire program is communicating to the operating system that the entire program exited with this error code. And then what you can have is an inter-process communication where if one program invokes another program, that program can communicate back to that other program that an error occurred and what type of error occurred. So the exit and ultimately return. Why do we return 0 now? No error, right? We got down to the end of our program and everything was great, right? That's what that 0 means. You don't have to if you don't want to. And in fact, these are far less standardized than internal C codes because it could be written in Java. Java has exit codes, right? Public, static, void int. You can change that to an int main and output an error code. You can exit with an error code in Java, system.exit. And so you can have a Java program communicating to a C program, communicating back to a node program, right? So that's kind of a way to do inter-process communication error handling. Other questions? No? All right, so the solution to those magic numbers was to use our own enumerated type, in C that is, right? Again, here's another example. Does the week begin with Saturday or Sunday? Sunday? Or sorry, Sunday or Monday is what I meant. Sunday? Okay, I'll agree. Here's another way that you can do an enumerated type. Type def enum, again. Now here I've omitted that last comma. You can omit that last comma if you want, or it's okay to keep it in there, right? And then finally, day of week, okay? The style, as you already noted, is to use upper underscore casing for elements. That is Thursday, Friday, Saturday. And if it has multiple words like we did before, to separate them with underscores. Generally, white space doesn't matter, but it's good to put them one to a line. And then we use upper camel casing for the name of the enumerated type. Now, an old school way of doing that would be to use lower case underscore. In other words, day of week would end up being, let me change it for you. It would end up being day of week. Right? That's an old school convention. I don't like doing that as much because what are you doing if you're doing underscore, underscore, underscore too much? How do you type an underscore?
Shift.
You take your pinky, shift, all the way over to the other keyboard. It slows you down already because you're traveling across the keyboard to do an underscore. But also, I don't know about you, but my pinky gets tired really quick. Right? Save your pinky. Don't do that. Use day of week. Right? It's much faster and it's much easier on your pinky. Right? You use type def enum. You provide a comma delimited list within the curly brackets. The name at the end ends with a semicolon, right? Because it's a declaration. Generally, they are declared in header files. Where did I put mine? In utils.h, in the header file. Why did I do that? Because I'm using it here in the source file, but I'm also using it over here in the lone.c file to check for those error codes. If I had put it in the source file, I wouldn't have access to them when I include the header file. So you generally put these things in the header file so that you can include them. Okay? So again, later in the program, what you can do is things like this. So today is Thursday, right? Yeah. There we go. Day of week today is Thursday. Tomorrow is Thursday plus 1, which would be Friday. Except that you can also do things like you can, but shouldn't, do the following. Today, or let's say a day of week when is equal to Monday plus Thursday. What is Monday plus Thursday? Friday? Is it? Okay. Yeah, it's not, well, in this case, it's not a day. right? But it is actually valid. You can also do something like this. Day of when is equal to, say, today, which again is Thursday, plus 500. What's 500 days from today? Oh, I'm sure that it's some day, but it's not going to be. It's not going to be that what you think it is. Right? It's not going to actually be 500 days from. The C is not that. It's not built into C to do that. It's not going to understand that you want a year and almost 2 years from now. Right? You would need an actual time library to do something like that, and it is built into C. But this doesn't work. Yeah.
So instead of like calling this enum type list, why not just use an array?
You could, and there are tricks to doing that too. Then you could use, because we haven't covered arrays yet, I'm not going to talk about it, but you can use the enumerated types as indices of the array to get string representations of the things too, right? And you can then use it as sorting. So for example, when we get to sorting, we'll do this, but freshman, sophomore, junior, senior, that's the traditional order, right? But if you were to order that as a string, what comes first? Freshman, sophomore, junior, so A, B, C, D, E, F, G, H, so freshman, then junior, then senior, then sophomore, which is wrong, right? But what you can do is you can develop an enumerated type, an enumerated type to have that proper ordering, right? The artificial ordering is what we call it instead of the natural ordering. To do something like that. So yes, you do use arrays sometimes, right? But then you use arrays in conjunction with the enumerated type because arrays don't have names, right? You wouldn't say Monday, you would say day of week sub 1. You wouldn't say Wednesday, you'd say day of week sub 4. And now you're back to magic numbers, right? Okay. So why are these invalid? And it's because of a dirty little secret in C that all enumerated types are actually integers. This is nothing more than fancy syntactic sugar. Right? It is the C compiler that is putting numbers in for you, right? So that you can read it, but at the end of the day, they're still going to be integers. By convention, actually by default, it starts at 0. This is why we put that no error first. By default, it starts at 0, so Sunday would be 0, Monday would be 1, Saturday would be 6. What would be 7? You've gone past your defined enumerated type. It is not an error. It is not a warning. It is just 7. So up here, when we went today, which is Thursday, what is Thursday? 4? Right? Yeah. 4 plus 500, that's just 504. And that's no day that you've ever heard of. Right? So you do have to be careful. Do not use enumerated types in numerical expressions like this. Just use them as in assignments. Use them in equals kind of like comparisons, like we did down here. This is fine. Assigning them is fine, right? Something like that. I'm not going to do that though. But using them in numerical expressions, knowing that they're integers, that's wrong. Don't do that. Okay? All right. So how do we do this in Java? Java uses exceptions, right, instead of defensive programming. An exception is an interruption of the normal linear control flow. Something, you're going along, command, something happened, right? You divided by 0 there. Okay, it raises an exception. Literally, it throws an exception. You try this code, and you're okay here, you're okay here, you're okay here. Something happens here, and an exception is raised and thrown back at you. You can catch it and then decide what to do with it. Right? And again, it's the try and catch. Those are the key words that are actually used in these programming languages. So which one is better? We'll take a look here in a second of how to deal with this, but you've seen them before already. With error codes, there's no semantic meaning. Yes, you can give it a name, a readable name like invalid principal, invalid years. You can read that and understand it, but at the end of the day, they're still just numbers. 0, 1, 2, 3, 4. There's no semantic meaning to any of that stuff, right? In fact, here, I'll prove to you that there's no semantic meaning to it. Let's go back over here to our C example. And now that we've changed everything, there's another potential error that we might have to deal with. Double star monthly payment. What's a potentially bad input for monthly payment now? Remember what Bret Hart said. Do not dereference a null pointer, right? So let's check for that now, because now we have a pointer that we should be checking for null. So by the way, that generally comes first, right? If monthly payment is null, then return a null invalid pointer. Invalid pointer. Error. And then else if. There we go. Okay. Invalid pointer. Well, I need that now. So generally, I like to put things at the end of the list. Right? Does it matter that I checked it first? Nope, because the enumeration takes care of it for me. I could put it second. I could put it third if you want to instead. Right? Is there any meaning to any of this stuff? The order? No, because at the end of the day, C will just simply assign, okay, year 1, year 2, year 3, year 4. There's no semantic meaning to it. Right? But in Java, there is. Right? With exceptions, you do have a semantic meaning. And what I mean by that is, let me go ahead and give you some examples that you've probably seen before. Null pointer exception, arithmetic exception, input mismatch exception. These are actual built-in types that are completely different, right? Over here, these are all the same types. They're all integers. They're just different values. Here in Java, these are actual different types. You would not be able to conflate these two types. You wouldn't be able to add them together. You wouldn't be able to treat an arithmetic exception as a null pointer exception because they're not the same thing. That's because over here in Java, we have what object-oriented programming. What we have is a hierarchy of these things. We have up here, we have all these exceptions. And then we have different types of exceptions. That's one type of exception, and that's a different type of exception. And they're not the same thing. They're all exceptions, but they're not the same type of exceptions. So here, it's a much stronger notion of error handling. Right? And there is a consequence to this, and I don't have an example to show you, but often defensive programming leads to these huge nested and separate error handling and go-to-fail type scenarios. What I mean by that is you've seen it here in the small. Over here in lone, I had to go, if this type of error, 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 and then do your actual work, right? With exceptions, what if I don't care if there's an invalid principal, right? I did input validation, and I don't ever need to handle that at all, right? So I'm not gonna. I don't want to handle that kind of that kind of error. With using this kind of approach, you kind of have to. You have to put all these big giant if else if conditions on everything. Over here with exceptions, you can kind of choose to try and catch it or not. Right? A null pointer exception, you don't have to surround that with a try catch because it's a special type of exception. Right? Likewise, an arithmetic exception, and I'm not sure about input mismatch exception. We'll go ahead and try it. Okay. So I'm going to go ahead and go over here to our demo. And let's start doing some dangerous things. We're going to go ahead and get rid of all this. All right. Let's go ahead and say int a is equal to 10, int b is equal to 0. All right. I'm going to try to divide by b. A divided by b. Right. And what kind of exceptions could result from this, by the way? A what? Infinity, so that's called an arithmetic exception, right? Yeah, there is not, unfortunately not. It's just one big, umbrella of arithmetic exception. Square root of -1, maybe. I'm not sure if that throws an exception or not. We could find out real quick. Math dot square root of a, and let's find out. All right, I have to go down the rabbit hole here. Oh, okay. It's making a call to the C standard library is basically a square root function here. That's what native code means. So I don't know. Let's see. The documentation does not say if the argument is nan or less than 0, the result is nan. So it just returns nan. It doesn't actually throw an exception, right? According to the documentation. So let's go ahead and get rid of that. But division by 0 does. Right? Let's go ahead and fix that up. All right, so let's try to run this. And you see that it resulted in that exception. We caught that exception, and then we chose how to handle it, right? By printing an error message here, right? Ignore this for now. Decide what to do here, though. Right? What other type of exception could occur here if I change this to an integer instead? Big I integer. It could be what? In a very special way. What if I set it to null? Can you divide by null? Nope. But that's not dividing by 0 either, because 0 is not null and null is not 0. So what other kind of exception could occur? A null pointer exception. NPE, say. Right? And then you can hit to do potentially handle this differently. Right? On the one hand, if it's an arithmetic exception, you could choose, one way of handling it, and if it's a null pointer exception, you could choose a different way of handling it. And in this case, did I choose to handle it? I didn't write any code, did I? Let me go ahead and show you that in fact it continues unabated. .println done. There we go. And it will print done here because you tried this dangerous operation of dividing by something that's null. Oops. Why is it? Oh, there we go. It went gray for some reason. Anyway, you tried this dangerous thing. It resulted in a null pointer exception. You chose not to do anything about it, and it continued right after that. Right? Okay. Let's try something else. Oh, actually, no. Let's do one more thing here. Catch. This is kind of a catch-all exception, E. Right? This block will handle any other type of exception. I can't imagine what exception would occur other than these two in this case. Overflow, maybe, I don't know. But you can, every exception, every type of exception, an arithmetic exception is an exception. A null pointer exception is an exception. So if you want to catch them all, then you can go ahead and just say exception. In fact, I can get rid of all of these and just simply catch an exception and print system.out println something happened. And we'll see here that the null pointer exception will end up being caught there. Something happened. The division by 0 will end up being caught there. Right? And an exception that's a catch-all. Yeah, go ahead.
So what if an exception, let's say there's two different arithmetic exceptions that can happen?
The first one that happens is the one that gets thrown.
Okay.
So if you have, I don't know, A divided by B plus A divided by B, right? There's two divisions by 0 here. This one will end up being the one that gets thrown because it's left to right.
Okay, and if it's like one arithmetic, one null pointer, then
Whichever one is first is the one that gets thrown, right?
And then, so if like two arithmetic, how do we, for the error handling, for the error method, how do we if they're like two?
You know that when you catch it, this is the type of exception.
So we wouldn't know what exactly would be wrong.
Well, you can print the stack. I think that I had this before, but you can go ahead and go with AE dot print the stack trace. What's the? Oh, this is a good opportunity here. What is a stack trace? Let me go ahead and expand this over, and let's look at the entire thing here. Oops, I need to divide by 0. There we go. And when I run this, infinity, look in the void. Division by 0, right? And where did it happen? It happened in demo.java, line 12. And this in this IDE, it's actually clickable and it takes you to that line, right? I'm hoping that this is a modern, this is Java 14 and beyond, Null. There we go. Let's go ahead and print that stack trace down here, NPE. There we go. Cannot invoke value because, yeah, excellent. This is modern Java. This is a feature that was added in Java 14, I believe. It used to be that when you got a null pointer exception, and you looked at this line and there were 5 things on that line that could have been null. Which one was it, right? And so you had to go into debug mode and you had to find out. Oh, it was the third argument that was null. In Java 14, they updated this so that it actually explicitly tells you what was null, rather than something was null, right? Okay, now it's B was null, right? The denominator here. So printing the stack trace can help. What is a stack trace, though? If this were function calling function calling function calling function, then it would print out that entire stack trace. Where did we hear the word stack again? The call stack, the program stack. Function calling function calling function calling function. It gives you the trace through all of those, so you know where the error occurred. The error occurred there, and how did we get there? Well, here are the breadcrumbs that got you there.
And then you can use that to modify your error.
Yes, yeah, to diagnose errors and then ultimately to debug it and fix it. Right. Let's see. Okay, so let me go back over here to the notes. There we go. So in Java, all exceptions, again, are subclasses. We're not going to get into object-oriented programming in depth yet, but they're subclasses of these throwables. Anything that can be thrown. There are 2 types of throwables. There's errors that are generated by the Java virtual machine. For example, if you run out of memory, right? There's no way the Java virtual machine can download more RAM, right? So at that point, it is a completely fatal thing, and the entire Java virtual machine dies. There's nothing you can do about it. And so you don't generally handle errors. But you can handle exceptions. Exceptions are a different type of throwable. This is what you do in your code, and there are 2 major types of them. There's exceptions, and then there's runtime exceptions. Exceptions are called checked exceptions, and runtime exceptions are called unchecked exceptions. With an exception, you are forced to surround it with a try-catch. With a runtime exception, an unchecked exception, you can choose whether or not to surround it with a try-catch. Now this kind of goes back to what we were doing in C. If in this function, if I chose to exit the program, does that sound like a good design principle? I'm taking the decisions away from you, right? If I design something with a checked exception, I'm kind of taking a decision away from you. I am forcing you to surround it with a try-catch. Does that sound like a good idea? The Java folks did 25 years ago. Since then, nobody else has really bought into that idea. And checked exceptions have remained something that are basically a Java thing. C++ did introduce them as an option. Very few people have chosen to take that option. Why? Because again, it's a bad kind of design. In fact, if you go back to the Java documentation on, you can ask, in the original Java documentation, there's a question of, okay, so when should you use a checked exception and when should you use an unchecked exception? It says, use a checked exception when you can, quote, reasonably recover from the problem. The problem is that the own Java people didn't follow that design principle. how can you recover from, say, no input? How can you recover from no internet connection when you're connecting to a database? How can you recover from a bad password? Right? I mean, there you can prompt them again for the password or something like that. But how do you recover from a file that you don't have permission to read? Right? Do you just guess at the contents of the file? No. Unfortunately, Java thought it was 25 years ago. Java thought it was a good idea, so they put it in the language. It's something you have to deal with. It is not something that ever caught on. It wasn't a good idea 25 years ago, and I think the vast majority of people have realized that it's not a good idea. The very fact that no other language has adopted this feature, I think, is a testament showing how bad of an idea it is. Right? But you still have to deal with it. For example, let's see. Let's go ahead and go with a scanner here. Let me go back over here to Java, sorry. Right, there we go. And I'm going to change this so it's 10 divided by 10, right? So we don't have any of the problems up there. All right, and there we go. I will go ahead and import this. All right, ignore this for a second. All right. So what I've done, and import file too. This is, we'll get to file IO later, but this is a scanner. I'm opening the scanner up to read from this input file called input.txt. I don't think I have an input.txt file. I hope I don't. Come on. Nope, I don't have any files here at all. So if I tried to run this, I would get a file not found exception. Let me go ahead and just print the stack trace here, e1.print stack trace, showing you that in fact that file does not exist. And by the way, here you see the much larger stack trace because main calls scanner, calls file input stream, calls open 0, and then finally that's where it finally found out that file doesn't exist. Right? So no such file or directory. Okay? I am forced to do something like that. You'll see here that I cannot compile without the error handling. It says undefined or unhandled exception, file not found exception. How can you reasonably recover from that? Make your own file, assume what the input is, right? It doesn't make any sense. So let me go ahead and undo this. And you are forced to surround it with a try-catch. So 25 years later, we're still dealing with their design mistake. How do we deal with it? So we're trying something, and then we're catching the exception. Any anglers out there? Any fisher folks? People that go fishing. Right? I'm not, so I don't know what that anglers is what they call themselves, right? So what do you do when you catch a fish and you don't want it? You throw it back, right? You catch and release. So what we're going to do is, instead of printing the stack trace here, we're going to throw it back. Throw a new runtime exception. Right? Now, what's a runtime exception? A runtime exception is an unchecked exception. Now, you're just throwing it back. If anybody wants to catch it, you can. If nobody catches it, it ends up as a fatal error. And what I'm going to do is I'm going to wrap that other exception around in it because I don't want to lose that information. What type of exception actually occurred? It's a file not found exception. So let's run this now, and you see that it is a file not found exception that was rethrown as a runtime exception on line 30. And there's my line 30 right there. You can choose to catch a runtime exception and handle it if you really want to, but now that choice is given back to you. I've just caught it because I had to catch it. I don't know what to do with it because there's no way that I can reasonably recover from a file not missing, and so I'm going to just simply throw it back at you. Catch and release my fish. Right? Throw it back at you. Yeah.
What if you just don't throw it back?
Then what happened before, we silence it. Right? Yeah, okay, error occurred, sit down, shut up. And nothing happens. Right? So you can do, that's another design decision, like, okay, file not found exception. But if you're actually processing the file, we'll say on line 30, then something bad is going to happen. Because scanner at that point will be null, and then it'll be a null pointer exception instead of a file not found exception, which is even weirder because why is scanner null? It's because the file didn't exist. And you lose that information by not handling it like this, by simply just silencing it. It's like they stood up and started yelling at you, file not shut up and sit down, and then, okay, now let's go ahead and process it. Now a null pointer exception happens. Where did that come from? What, you don't know where it came from because you silenced the only thing that was telling you what was wrong. Right? Okay? You can also build your own exceptions if you really want to, but we're not going to do that. Yeah, I don't think that you do that in any of your hacks. But there is one other thing that you should be made aware of. So you can try, you can catch, you can rethrow, but you can also finally do something about it. Finally. So finally is a block of code that is, this block of code is executed regardless of any exception. So an exception occurs, it still executes. An exception doesn't occur, it still executes. Why would you want something like this? Here's a scanner. Some of you have asked, do we on your I think hack 2 or something like that, where you open a scanner to read from the standard input, and you got an error. You got a warning by the Java compiler that you didn't close it. Right? So this is a perfect place to actually close your scanner now. Right? Oops. I have to declare it outside here. Scanner s is equal to null, and then s is equal to new scanner, and regardless of what happens, close it. Right? And you can also say if s is not null and s dot is closed, or is closed, s dot is, nope, it doesn't support that, dot, s dot closed, nope, all right, fine. I just want to make sure that it's null so I don't invoke yet another null pointer exception, and then I'll close it. Right? If it's not open, if it's already closed, I think that this is a no operation. That would be my guess. Right? But why would you want to do this? Suppose that you open up the file. It's fine. There's no, if file is found, there's no exception there. But then you start processing it. Maybe you read, you're expecting an integer on the first line. So s dot next int. Right? Int x is equal to next int. But it's not an integer. It's hello. Right? That would result in a type or input mismatch exception. In which case, okay, well, I'll handle that, but also my file is still open. I need to close it. That's not going to happen if you put close right here, s.close. If an exception occurs on 29, control flow jumps down to the catch statement. Catch. Oh, what was it? I had it over here. Input mismatch exception. IME. Get rid of that. Sorry. There we go. Fix that up. And then to do handle. There we go. And I have to import it. Come on. There we go. All right. So suppose that we have bad input on line 30. Do we ever get to line 31? Nope. Because an exception is thrown. Control flow is handled down to line 35, in which we handle it, and that file was never actually closed. But if we put it down here in this finally, a block of code that is executed regardless of whether or not an exception occurred, now we have that guarantee that it is still closed. Okay. So we have try, catch, rethrowing, and finally blocks. And most of these things are going to be optional, especially for unchecked exceptions. If you ever write your own exceptions, make sure that they're unchecked exceptions. Right? Don't force somebody to surround everything with it. Because if you force somebody to do code a certain way, just out of frustration, they're going to do it the wrong way. I can tell you that, right? That the people will not do the right thing when they're told to do the right thing. Yeah. Why can't what?
Like, why should we close the scanner?
99 times out of 100, it won't matter. It's that one time that you opened up the file, failed to close it, and the act of not closing it has corrupted the file. Or it happens more often with file output. You're writing to a file, and there's something in the buffer that didn't get pushed out to disk. You end up closing the program ends, that buffer is lost and not saved to the file. But if you close the file, it empties out the buffer, makes sure that everything's in the file, and it's not corrupted. So it's best practice. Now, we did not take off, I believe, for not closing the standard input because it's not a traditional file that you can open and close. It's a system level file that is always there. Last question? Yeah.
So, in the code that you wrote on top, so that there, the one, yeah. So there's a scanner, and then there's also that reads the scanner.
Yep, it's expecting an integer on the first line of this file, input.txt.
There's going to be two different.
There could be.
Two different exceptions.
Yeah, in this case, which one will happen in this case if I run it again? Which one occurs first? The file doesn't even exist, right? So suppose that the file did exist. And to do that, I'm going to have to go with data / and create a new folder called data. There we go. And in that folder, new file called input.txt. And let's open it up and go hello. Right? That's not an integer, right? So when this runs, get rid of old stuff here. There we go. Now when it runs, the file does exist. So no exception here. But that first line is not an integer. So, oh, come on, really? Input mismatch exception. Throws input mismatch if the next token does not match the integer regular expression or is out of range. If the input is exhausted, if the scanner is closed. Okay. System.out.println x. Oh, you know what? It's because I'm not doing anything. All right, so let's rethrow that one too. And you'll see that it actually, IME, there we go. You'll see that it actually gets thrown. There we go. Right.
So when it's like that, are you forced to have two different exceptions? Can't attach two
If you want to do different things, yeah.
Okay.
If you don't want to do different things, you can just catch all exceptions and then do whatever. Or in the event, in the case of unchecked exceptions, you don't even need a try catch, right? Unless you want to.
Okay, but in this case of check exceptions, do you need to check both of them?
I think file not found is a checked exception. I think that input mismatch is a runtime exception, so you don't need to. Yep, it compiles. All right, somebody wants to come in, so we're going to have to say goodbye.